Yeah, hi everyone. So I did a quick pivot to the original.
Wait.
Oh,
Can you share the screen from
oh
Zoom?
no,
Yeah.
I bet.
How do we
Okay,
go?
where's our call here?
I think we need just to share the entire screen. Right, we cover where were you? Here.
Yeah. Okay, so now we're we'll guess. Okay.
But now all of that stuff needs to be moved around.
Uh,
You want to do it since we have the driver's seat.
Yay. There's a way to hide this, right?
Hide floating meeting account. Oh,
Okay. Okay. So, hi everyone. Yeah. So the original plan had been to talk about deep learning and embodiment, which is a concept in cognitive science and philosophy of mind. But after going through that paper that I originally proposed, I was like, oh, there's a lot of background. There's a lot of sort of explaining I'd have to do. It'd be like a lot of like an hour of talking about like mostly background and then kind of just going through their paper quickly, which is still interesting, but it was too much work. So I decided to just pick a NeuroBOLT paper that I thought looked interesting from last year. I'm excited for the new round of papers to come out in December. It'll be interesting to see what best paper is and all that good stuff. But this is from last year. Uh, Specifically, architecture, where the authors are looking at translating EEG signals into functional MRI. At its core, the problem setting is quite simple. So let's just look at what they're doing. So I thought it was an easy kind of problem to understand. The architecture is kind of interesting, and if you guys want, we can kind of look at the details. That's what I ended up being fascinated by was kind of some of the training details and how they set up the model and all this stuff. So I think we're all kind of familiar intuitively with these two modalities. They're quite common in our work. So electroencephalography or EEG is a type of data where you place electrodes on the scalp and they are measuring electrical activity at the scalp level, right? So you're actually measuring these electric fields that come from populations of neurons firing within the brain. And there's a lot of work done showing how this can be useful for measuring a lot of like oscillatory behavior and the famous alpha, beta waves, gamma waves all come from EEG research. And looking at that, you can find them in magnetoencephalography as well. But EEG is sort of the origin of that. And the characteristic that's important for this work is that it's low spatial resolution, right? You have some number of electrodes on the scalp. So in this paper, they talk a lot about having a model that generalizes across different numbers of electrodes. I'm going to kind of contest that claim based on their experiments, which I found pretty inadequate for supporting that claim. But we can talk about that later. Um, but uh, but yeah, so you can have some number of electrodes on the head from 16 to 8 to 64, 128 on really high resolution caps. Um, and some stuff that's interesting that we do here at the lab is with those really high resolution caps, you can actually do source localization like you can with MEG as well, and you can actually get without doing any deep learning, you can just use signal processing techniques to actually get the region inside the brain where that EEG signal is believed to originate, right? So with really high resolution, you can do cool stuff without even thinking about deep learning. But this is first where they throw a deep learning architecture into the mix. So we'll talk about that in a second. So we've got EEG, low spatial resolution, high temporal resolution. So you'll have often long scan sessions, 5 minutes, 15 minutes, and really high frequency of measurement compared to functional MRI. Functional MRI, which we're all more familiar with here, they are talk about in the paper about fMRI as having high spatial resolution. That is true, of course, compared to EEG, which has much lower, on the level of 16, 128. We actually have 3D volumes that we work with, and we're all familiar with 3D volumes that vary over time, blood oxygen level dependent signal, this idea that, vasculature in the brain, the brain is highly vascularized. So as neuronal activity increases, you'll have increased blood flow to these regions. And there's a lot of confounds and discussion about sort of what meaningful signal is in fMRI. It's been a long debate over a period of decades now since the original papers and since been sort of publishing, whether or not there is real signal in fMRI. I think it's pretty definitive at this point that most people are on board with task fMRI at this point, and then rest fMRI is a lot of more people are on board with it as well. Uh, where you don't have some particular task that the person is doing in the scanner; they're just sitting there. Uh, but still, you'll still find some people out there. I've been at conferences and talked to people about resting state fMRI. They're like, "It's all garbage. It's all noise. There's no signal in there at all." So you'll still meet people that feel that way. And then yeah, so it's a higher spatial resolution than EEG, still lower spatial resolution than structural MRI, of course, and some of the other modalities that are higher resolution in space, but lower resolution in time compared to EEG. That's the important kind of thing to remember. The paper they talk, they're presenting this to NeurIPS 2024, so they're giving a lot more background about EEG and fMRI. I kind of talked a little bit about these pros and cons and stuff that they right. Yeah. So there's they kind of mention a lot of the stuff that I talk about that I already talked about. Yeah. So some of the pros of EEG that they highlight: it's a direct measure of brain electrical activity, high temporal resolution, cheap, easy to collect. That's a big benefit for a lot of clinical applications, and a lot of the companies that are getting into neurosignal study as well are doing EEG style data. So Apple's patents on their little earbuds that act as EEG electrodes, or building on principles from EEG. That'd be extremely low resolution. You have two electrodes, right? Yeah, so a lot of people, because it's so cost effective, a lot of people are working with EEG. Highly portable as well, of course, versus functional MRI. You need a big magnet that's super cooled and extremely expensive. Some downsides there is extremely expensive. People tend to not like sitting in that scanner for a long period of time. So, certain patient populations, it can be an obstacle. Certainly with children, it's an obstacle as well. Sometimes having them sit in the scanner and be very still versus putting on an EEG cap where you still want them to be still, but it's not as much of a problem. Yeah, so they're talking again about the hemodynamic response is still like a lot of people have they get their hackles raised when you mention fMRI and talk about hemodynamic compounds and stuff like that. So there's a lot to kind of look at here. So their approach, what they're proposing to do in this paper is, and I wanted to have a discussion about this because this is, I've proposed similar work to Vince and to others before, and what I kind of get a question of, what's the point, right? Why are you doing this? And I wanted to kind of centralize that question in our discussion here. So the proposal that they're doing is they want to reconstruct functional MRI data from EEG input, right? And so does anyone have any sort of thoughts as to why that might be useful or interesting, right? So certainly there's the biological argument and the signal processing argument, or just the modeling argument. Like, it's an interesting modeling problem. Can I do it? Right? Can it be done? And the answer is, well, yeah, it seems so within some error. But yeah, is there any potential what do you think the use of this could be beyond just, oh, it's there, I can do it? It's a transformer style problem. Yeah.
I think it would be interesting to see the difference in maybe for glia going forward, just because a lot of the glia are involved in the action potential that we see over time with the fMRI. We don't always capture those in certain tissues with the with fMRI. So I mean,
how do you think EEG would get us, translating from EEG to functional MRI would get us a better insight to glial activity?
I think being able to see the space as opposed to just the action potential, because it would be a lot more helpful.
Okay.
Just because not all glia are the same proportion involved in the generating action potential.
Okay.
And so I think that would be really useful for differentiating the two. That's my thought. Initially, it could be completely wrong.
Yeah, I guess I'm not immediately clear how that would translate to this particular application, right, where you're translating from EEG to functional MRI. But any other thoughts from people?
Well, I mean, you said it was much cheaper to collect.
Right. So that's one
so
thought.
If you ever need,
right,
any sort of prediction research, whatever,
right,
easier or cheaper to collect EEG and then transform.
Right, right. So that's I think that's like an interesting insight, right? Is that the whole argument against functional MRI in clinic is that it's so darn expensive, right? And it's again, it's an obstacle for certain patient populations to even get them to sit in a scanner. There's a lot of obstacles to functional MRI beyond just the cost as well. I think that is a potential interesting application of this style of translation model between modalities. As if one modality is extremely cheap, modality is extremely expensive. Uh, I think my question then is, what would it take for you when you're looking at a model like this in an experiment, set of experiments? What would it take to convince you that that model is able to do this in a way that would be interesting in clinic? Right. So you want a model that is able to take anyone's EEG, right? That's not just on the patient population that you're interested in. And I'll highlight that. So their data set in this project, did anyone else look at the paper at all?
Yeah.
Yeah, you looked through it, or even just glance through like the results and stuff. So the patient population, spoilers, is extremely tiny for both of the experiments that these guys do. You have really high temporal resolution, but I think both of the data sets that they evaluated are less than 50 people. So it's a very tiny patient population, right? So at least for me, when I look at this kind of paper and I think about that potential impact, I'm a little bit like I would expect to see a much larger patient population in order to like see that potential benefit kind of embodied in the experiments. Because certainly you could say like, if these people had infinite subjects, that would be a nice impact. But yeah, that'll be one thing I'm going to kind of bring up against this paper that I think is they don't substantiate that at least benefit for me. So I'm a little bit unsure of the practical implications of this kind of work.
But wouldn't it be?
Yeah.
Did you have a question first?
Oh, I was just going to say it could be useful for like increasing like sample size or the power for certain meta-analyses if you're going from this fact that like, oh, well, we can translate these back and forth. Well, if you want to corroborate something in the EEG domain, well, now you have access to data from the fMRI domain that you can translate.
Right. So that's a good insight as well. So filling in holes in studies where you have EEG and fMRI for some subjects, but maybe not all of them went through the fMRI. Maybe the fMRI was added on as an add-on grant later in the study, and you're like, oh, I want to get an idea of how functional imaging retrospectively would look in the rest of my population from earlier in the study. So that's potentially interesting, and one where at least the translation between study populations wouldn't be a problem. Yeah. Any other ideas or
Yeah, but the question that you started with, that fMRI doesn't contain any neurophysiological signal.
Right.
Well, if you can go from EEG, that's kind of an evidence of maybe fMRI contains that signal because you could obtain it
as well.
But then I don't trust any of the results here for the following reason. fMRIs claim to be spatially more coherent EEG inside of the brain. EEG inside of the brain, I don't trust at all.
Yeah.
Volume conduction, blah, blah,
exactly.
blah, so how could you from EEG? Yeah, maybe you can catch the waves, but you don't have the locations. But if you catch the waves, why do you need fMRI of that sort at all? The only advantage of fMRI, how noisy it is, and all this temporal inverse problem that nobody talks about, but it's there. It's not just delay.
Yeah. So they bring up the volume conductance specifically, but they only talk about it in terms of like kind of presenting the two modalities in the background in the paper. So they introduce this problem with EEG, and another pet peeve I have with this paper is that they don't incorporate that then into the method at all. Like there are a lot of ways in EEG connectivity analysis, for example, to get around volume conductance, specifically by doing phase-based connectivity and stuff like that. It's not really that it's mentioned. Maybe that their argument is that somehow the spectral part of the model that they do, and let's talk about that maybe and get to the methods, gets around the volume conductance problems. But yeah, it is I think unsatisfactory from that standpoint as well. But it does also provide, I think, what you said at the beginning is also right. So that it does at least show us that there is some neurological signal in a functional MRI. So the skeptics, the hardcore skeptics of fMRI, I think, don't have ground to stand on anymore. And I think that's widely recognized, especially for task. They'll still sometimes meet resting fMRI holdouts, and then again, when you try to do any dynamic analysis, you'll get people that are like, oh, like within certain time windows, you actually can't show anything of interest. But that's it is what it is. So. Okay, so let's look at this approach. So this diagram, I think, just describes is a high level describing the problem that they're doing, and so they're translating between these two modalities. It's quite if you grew up reading the transformer literature, if you've read the canonical papers, it's quite similar to the seek-to-seek style problem, right? And they mention seek-to-seek style models as baselines. They don't really do a lot of comparisons with those style of models. But yeah, so if you're familiar, it's very similar to translation style problems, but now you're translating from modality from one modality to another. Okay, so let's talk about this approach. Okay, yeah, so this is quite standard in so a lot of approaches have been using EEG with transformer style architectures, and in terms of what this paper is doing, there's not that much interesting just in the kind of the time series analysis branch, other than the spectral analysis that they do. So they do a straightforward tokenization, just a window-based tokenization. And they have a normal spatial embedding. I think it's just a cookie cutter sinusoid spatial embedding, or nothing like crazy complicated. A temporal embedding as well, and they have a spatial embedding and an embedding in time. So they're embedding the electrode space and the temporal space, right? Okay, so. Yeah, let's maybe take a look, because looking at the paper might be more helpful here than looking at their high-level overview. If you're ready to kind of talk about this, let's kind of look through as well if you want to talk about. Right, so this is, in this dimension, they just have each of the channels from the EEG. And so they're just breaking it up into temporal windows. They have this temporal convolution branch, which gets fed in along with this multi-dimensional position encoding, which I want to talk about separately, into a transformer encoder with average pooling. Just a normal addition here with the spectral feature embedding as well, which we can talk about in a second. So the spectral embedding that they do is, I think, a little bit interesting, but it's methodologically quite straightforward. They just, again, take differing window sizes, take the Fourier transform, and feed those in, get separate embeddings across different resolutions for the Fourier transform, looking at the spectra. So it's nothing particularly complicated, but it's an interesting kind of quick methodological branch that they add on. And they didn't do much in terms of ablation to show, at least as far as I recall, that this branch adds in a whole lot performance-wise, but it's an interesting kind of approach. And then let's see what else is there to talk about in terms of the model. Okay. Yeah, okay, so let's look at the paper and talk about this multidimensional position encoding, because this is something I wanted to kind of pull apart a little bit with you guys. I want to hide the video panel so I can get up to my card.
I think if you click on more and the last one, yeah.
Okay. All right, so let's take just a look at the paper and fill in any detail that I missed from my glossing over. Okay. All right, so yeah, the spatial temporal representation I think is interesting, right? So yeah, so they just have the EEG signal, channels by time, nothing super complicated. Yeah, so window size and stride. Okay, yeah. All right, so just patch embeddings. Okay, now what I'm missing is.
And they talk about spatial temporal. There is the electrons are on the surface, right? So there is proximity in like sort of geodesic distance rather than 1 through 21 or whatever number of elements they're using. So I wonder if they're taking into account that graph of.
Yeah, it's not entirely clear. This is like, when I glimpsed through the paper, the detail on the spatial embedding must be in the appendix.
Yeah, I'm a bit confused as to how the EEG time series is like incorporated with the fMRI as input to that model. Because I see like they're cutting the EEG tokens, but then
Well, I think they use the fMRI as output, right? So I don't think the fMRI is input anywhere in the model. So it's only it's EEG to fMRI translation, right? That's the idea. Similar to you do like German to English or English to German, the seek to seek style problem. Um, So this was a detail that I missed in the main paper was how exactly the spatial embedding worked, because the temporal embedding is clear, like they have patches based on windows. It must be just like a grid style visual transformer, but maybe I don't entirely understand. Like how would you grid uh, electrodes?
Yeah, electrode.
they're treating maybe the electrodes as regions. Each electrode has its own time course.
That could be.
Well, at least they're clear with the limitations. They have a whole section of limitations.
Yeah, sometimes there are papers they claim they have it, don't. But it's spatial. Yeah, I missed. Airlines visual embeddings. Yeah, they don't say how they get this. This might be based on the foundation model that they use. So maybe they're just like going to cite other paper for that. So sorry that that's not clear to me, but they don't talk about it in their paper at all. But what exactly? But the idea is you get a spatial embedding across spatial regions across electrodes. You get a temporal embedding. You combine those into input that then goes along with this tokenized EEG input into the transformer. It's a bit weird. Yeah, I don't entirely get why this second branch is doing what this second branch is doing, but it's based on some previous foundation model that they don't elaborate on, I guess, is the what they're doing in here. But yeah, so other than that, so the model that they build off of is, so where did they mention the name? No, NeuroBOLT's their model. LeBron, so there are a few different EEG foundation models that are circling out there. LeBron is apparently one of them that I haven't particularly heard of. I imagine it's from their group, is my guess. So that's probably why they don't explain exactly what this multidimensional embedding is. But so yeah, so I mean, I think other than maybe some detail on how this multidimensional position encoding is working, I think the architecture is rather straightforward, right? It's just a normal transformer head with this multispectral feature, sort of additional perspective concatenated in as an additional kind of modality is how I would kind of treat it. And then they're predicting, they're doing mask-based fMRI prediction similar to what the brain LM style foundation models do as well. Just again, just masked it output prediction, and they start with task MRI, task fMRI. So yeah, let's look at their results. So these are R squared values from. So they're projecting within subjects and between subjects. They have a whole section talking about those two kinds of experiments that they do. And it's a very small data set. So yeah, less than 22 people with 29 scans, each 20 minutes. So a lot of data temporally, but very few participants. Yeah.
Did they ever explain why it's so small? Like
why the data set
do they
is
have
so
a
small?
rationale for why? Yeah.
Well, they don't talk about it. I would imagine it's just due to cost and what they might have done it on pilot funding or something like that, or smaller 21, or they're using an existing. A lot of the tasks simultaneous, so they're using simultaneous task and fMRI, right? So that's because of the fMRI, usually are doing that with grant funding. And it might have just not been from a large study. But
Do they talk at all about leave subject out, or like how do they do this cross validation? Do they use the same subject in test and train?
maybe more in the yeah, they didn't talk about it in the main paper, and I didn't read the supplement.
That's kind of also important to generalization, right?
Right.
If they generalize within the subject, like we train on 50% of the same subject and we test on the other 50%. It's much easier inflate.
Oh, so these are quick correlations with that. Yeah, they didn't talk about it in the main body of the paper. We can look at the appendix here real quick.
Yeah, like how do they do that train test split? Because that's. I assume the other numbers they didn't retrain the models; they just took them from the paper straight at their model.
Probably just do the fine for 30/70. Maybe that'll show up.
Okay, for subject-specific prediction. Okay, I must.
Oh, they split the same scan.
Yeah.
So they don't test across the subject.
Well, this is subject-specific. Yeah, so that's for the subject-specific. For inter-subject analysis, they don't talk about where's the intra. Oh, inter-subject. We randomly divided data sets into training validation by 1 to 1. So 18, 5, and 6 for the task data. So they do split across subjects, it looks like. I imagine. Since data 2 scans aren't sure to be in the same set. Yeah.
Okay, that's good.
Yeah. Right. So these are correlation values. So these are quite low. I mean, so if you want to try to beat these, right? It looks like the baselines are barely above 0.5 correlation. But yeah,
I don't understand what this means at all. Like EEG comes from the topography, the entire head surface.
Right.
fMRI comes from the entire head volume, and there will be different time series depending on the region.
Right.
What are they generating?
Well, they're generating ROI time series.
Which ROI?
For these specifics, so they have it's based on an atlas, that specific atlas. I forget the name, but they chose an atlas.
So they're generating all of them.
Yeah, they're trying to predict each, and I believe they're doing them all at once. That was my understanding. Let me look.
Also, I don't understand how this is leveraging EEG advantages of having more time points. So they're predicting the exact same number of time points for the fMRI series.
Yeah,
they're losing that information.
Yeah, they're not. I mean, they're predicting they're using the entire EEG scan. I think they're the fact that a lot of these papers that I see at NeurIPS, these people don't understand the neuroimaging data deeply. They have usually enough to talk about the background, and they will mention confounds and stuff like that, data problems, but then they don't seem to actually do anything interesting from a neuroimaging standpoint. What I would expect is you take a sample of the EEG that corresponds to part of the fMRI time series, you use that to predict that. And so you generate more samples that way as well, would be my understanding. But it seems like they're taking the full scan and predicting their full EEG time series and predicting a very low temporal resolution fMRI region, which it doesn't make any sense to me either. It's I think if someone wants to work with simultaneous task and fMRI data, talk to Subik. Maybe he can give you access to it. I've talked to him a little bit because I'm interested in problems like this, even though I don't entirely see the practical upshot unless you have a very large data set, which we just currently don't. But yeah, I mean, they obviously show that their model outperforms baselines. I mean, some are, not entirely within standard deviations, but pretty good performance overall. No real ablation study, which I was missing, not even in the appendix as far as I saw. Or actually, there might be in the appendix.
Just a transformer encoder, come on.
Right.
With
They talk about the spectral multi-scale stuff, and they talk about this like this.
This is for how they do embedding, right?
Right. Well, the spatiotemporal embedding as well as they talk about like an innovation that they do, and spatial and temporal embeddings are not new. For multi resolution spectral embeddings are not new. They combine them and kind of are claiming it's a new approach. This is what I see in neurosupers all the time. They just take a bunch of like puzzle pieces, put them together, say it's a new architecture. Don't really do an ablation study, apply it on brain data, have a bunch of really cool brain pictures, and then get published. And this is kind of what this paper is to me. It's a harsh to the authors out there. I think it's an interesting paper. But I'm just like, it's like, I think there's more that could be done, right, from a neuroimaging standpoint. I think this paper.
Yeah, it's a different conference. It's
right.
different standard. If you submit this to a neuroimaging journal,
right,
completely different
review.
So,
yeah. So I mean, I think they like the set of experiments is convincing. They outperform the baselines. It's interesting. Critically, I'm a little bit underwhelmed from a neuroimaging standpoint. It's my kind of overall take on this paper. I think the populations are small. It's not a problem. It's not the author's fault or anything like that. But it's just like you can't like the impacts of this kind of model and the interest of this kind of problem are not really highlighted. Yeah.
Sorry, not to put you on the spot, but then how would you propose, like, as a neuroimaging, engineer, how would you propose actually doing this?
Like what's
from that standard? From that standard.
Well, so there are a few different things. So I mean, certainly the population size, I think, is not addressable. Like if I was reviewing this paper and mentioned population size, they would probably just say like, this is the data that's available. fMRI is expensive. Certainly, combining from multiple studies and showing you could translate from one study to a different study would be interesting. If you can get access to more participants, I think that would be more convincing. There are a couple open neuro data sets with simultaneous EEG-fMRI. They're not huge either, but they would at least just show like on other data. So just from a data perspective, it's a little bit like there are some resources out there to find more. From a methodological standpoint, I think what we talked about with what Joanne brought up, where you're predicting, you're trying to find some correspondence between windows of EEG and functional MRI. Temporal alignment can be difficult because there's this hemodynamic lag in functional MRI as well, and they talk about that. But then they talk about a lot of problems with these imaging modalities, right? The hemodynamic lag, the volume conductance in EEG, and it would just be interesting to see methods that are actively addressing those problems. And maybe their claim is that the spectral features do address that problem, because that's typically what I'll see for volume conductance, is that you can look in the frequency domain and come up with at least connectivity measures that avoid the volume conductance problem. But they don't experimentally demonstrate that their approach does that, right? They don't have a study without the spectral embedding.
So there is a way to rephrase this in the modeling tradition, where the model didn't just mean matrix multiplied by another matrix, like a model of how things works, like a physical model.
Yeah.
So EEG and fMRI, they both measure what's going on in the brain, right? So let's assume it's cortical activity of pyramidal neurons, and for EEG, it would detect. Well, EEG actually would detect everything, but in a mixed points. So we can build a forward model of neural activity in the cortex on everywhere in the fold, and how it will reflect in the EEG and how it will reflect in fMRI.
Yeah.
And then we will need to invert EEG, but it's an ill-posed problem, blah, 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 lots of stats problems, and then use that activity in the brain. Now we can model fMRI with a simple HRF for differential equation system of four equations, maybe slightly more, balloon with Windkessel model, basically, and we're done. So it's kind of possible. There are tons and tons of uncertainties, unknowns, things like that. And the claim could have been here, hey, look, deep learning model does all that implicitly, right? From EEG, inverts it back to the brain. But then what I would like to see is that I know EEG wouldn't detect that well anything deeper in the brain. So can they show that, or can we see from that data that the deeper ROIs have worse feed and the surface ROIs have better feed and like stuff like that with this story of what the actual common activity that produced both of them. Both of them are highly indirect measurements of what's happening in the brain, and I don't know which one. I don't like them both. So, yeah, but I don't know which one is better. I think MEG would have been better than any of them, but
Yeah.
problems everywhere.
I think it's just, I think there's a lot more that could be done here. And I mean, I think it's interesting, but a more neuroimaging rounded paper would have more experiments along the lines of what Sergey is saying and what I was describing as well, I think. But just to kind of move on to summarizing their results. So they don't do an ablation study in terms of architecture design, but they do talk about some different training strategies. So that's at least I think worth talking about, because that's a lot of the LLMs these days are edging out on one another by what kind of fine tuning they can do and how well they are when you fine tune them to do specific tasks and that kind of thing. So at least so the experiments that they do are translating from so this is their generalizability claim, is that they're training on resting state data from the same population and then translating to a task-based data from the same population. So again, not entirely generalizable in a population sense, but at least from resting to task, they're claiming that they can generalize. They do outperform baselines that as well. Well, actually, did they compare baselines for generalizability? I don't think they did. Yeah, but this is more where they did just the comparing the different training strategies for generalizability. So it's a little bit like kind of pieced together strangely, in my opinion. But they showed that fine tuning, with on the task data will sometimes help the model be able to better reconstruct certain regions, which is a little bit of an interesting result. I don't think it's that interesting. I just I don't think this is like it's interesting that different fine tuning strategies work better and worse for generalizing from rest to task. But again, it would be more interesting if this would generalizing to totally unseen population of EEG data. Like they claim that they can generalize to different electrode montages, but I don't see any experiment demonstrating that in this paper. Like generalizing between electrode montages is a pretty big problem in EEG, not only because you'll have different numbers of electrodes, and there are kind of cap standards where different electrodes will go, but there is variation between the kind of cap you'll get. Sometimes the montage will be in a slightly different place on the scalp. And so I think that would be a really cool demonstration that they could have done, would be to find two different montages and show that you can take two different montages input and reconstruct the fMRI perfectly well. But they don't do anything to demonstrate that. So it's a bit of an empty claim in this paper, in my opinion.
Well, you can be sort of give them benefit of the doubt that it's a first paper to ever do that.
Right, and probably what they mean is just that you can't in the deep learning sense, because deep learning is so modular, you can just plug in different numbers of feature spaces and they'll all work, which is probably all that they meant by that. But which is I mean that's just the benefit of deep learning in general, that you can do that kind of thing. So I guess not that interesting to me. But I think an interesting little paper. I think. Does anyone else? I've kind of just been talking for a long time with Sergey, kind of chiming in here. Does anyone else just have any thoughts or questions about this approach? I think, if we had the time, I might click over to this other foundation model paper and see if we can figure out what this spatiotemporal embedding is, because I'm a little bit at a loss. Let me see if let me talk about it somewhere else.
Like reference 22 kind of.
I think that is we just look at the spatial. Okay, here it is in the it's in the appendix. Okay, similar to. Oh, this is different. This is something different. Yeah, this is different. Yeah, okay, they don't talk about it. Yeah, so let's look at that reference 22. Let's see if we can figure it out. But yeah, any other questions, any other thoughts, concerns, complaints, criticisms, insults?
I mean, ultimately, I think it would be cool to see this approach where the output is the fMRI signal with the same temporal resolution as the EEG.
That'd be really cool.
Yeah,
I mean, you don't want to have ground truth for that, right?
Yeah.
So, yeah, so there is no protocol in functional MRI that can get as fast of a frequency rate, excuse me. There is no protocol in functional MRI that can get as high temporal resolution as EEG. EPTI and other undersampling techniques that exist out there do increase the temporal resolution, kind of.
But that is trade-off.
Yeah,
But this resolution fMRI will be mostly flat.
right.
It's like comparing speed of light and speed of how blood flows. It's like there's stuff happening in blood is coming there slowly to feed them. So the kilohertz, yeah. But although people claim that 100 hertz is like as fast as we actually need to measure. So all this all of this is filtered because neurons cannot do it faster anyways. So the faster than that is just noise, but we still collect faster, so we can filter and work with that signal. So
Okay, so this is the foundation model EEG paper. I might send this into the chat as well. Yeah. Okay, here we go. Temporal and spatial embedding. Utilize temporal embedding and a spatial embedding, both of which. Okay, so they just, it looks like the others of the second paper basically just copied this verbatim from this paper. Not
are they
verbatim.
the same authors?
No, that's actually, I'm surprised. I thought they would be, but it doesn't look like.
Shanghai, it's like just the place we need to connect up. No, and they're but maybe there are people with the no different people.
Yeah, I think it's different. Which I thought for sure because I hadn't heard of this. I've heard of a couple other EEG foundation models, but it looks like they're specifically targeting BCIs. So that's interesting. But it'll be interesting to look at this paper. There are a lot of new foundation models coming out, and they all claim to be the best. And they still don't talk about the spatial embedding. Exactly that means. Oh, okay. I see. Okay, I think I get it. Okay, so it is, yeah, so they're just taking, so it's similar to a vision transformer, right? But they're now just taking spatial embeddings across the electrode space, kind of like, so if you kind of arrange the electrodes in a grid, you can have spatial information about where the patches are taken.
So some kind of some Mercator projection.
Yeah, something like that. Yeah, exactly. Yeah, so it's got to be something like that. Yeah, it's a little bit. I wish there was more detail about how exactly they determine that. Like if they are using it in the montage space, or if they are just arbitrarily kind of assembling the list of EEG electrodes. I imagine it's more principled than that, but yeah, missing information. All right, well, cool. Yeah, any other questions? Does anyone have interest in this kind of project? I know, Joanne, you expressed some interest in it, and yeah, if anyone wants to, I posted the GitHub for this code. It'd be like I'd like more like. It'd be fun if more reading groups, like when we get the GitHub, are just like, oh yeah, let's take their code and apply it on some data, and then think if there's something like some small tweak we can do to publish a quick paper. Like that'd be a fun little thing to do after more reading groups if the code is available, right? So the GitHub is posted on the reading group channel, and
we have a lot of data.
Yeah, we have a ton of data. Yeah, we do. We have MEG as well.
Blaze somewhere over there who sits on this.
Yeah.
Just have a repository from all of our reading group GitHub codes. So that'd be interesting to sit in there.
Yeah, yeah. If you want to, maybe on the reading group website, we could just add like a link for their GitHub as well. Just as an additional link. Yeah, if anyone wants to work on this, I don't have time to work on this and apply it to data, but if anyone wants to try it, we can talk and get a little project going. Yeah, I think it's interesting. And again, to the authors, if you're watching this, sorry about overly critical of the paper. I think it's a good paper overall, maybe missing some detail. I would have encouraged to resubmit if it were me, but
It's
that's
already
just,
published.
it's already published.
They've got lucky. You weren't.
Yeah, they got a good paper. Yeah. All right, thanks, folks.
Yeah. That's very interesting. I have a kind of like in this thoughts that this paper inspires. It's just again an inverse problem and modeling.
Yeah, we've talked about it a little bit before.
Yeah. We work I worked with the multimodal inverse problem solving. If you have fMRI and EEG, can you reconstruct what's going on in the brain that caused both of them?
Yeah.
And then if you can invert it into the brain surface or into the brain space, because again, temporal inverse problem in fMRI, you never know when things happen, really, compared to how fast neurons operate. And spatial, like there is uncertainty, spatial uncertainty in EEG even. EEG is just a nightmare. Sorry, EEG people who's listening to this. So maybe we can replace this inverse problem solver with intuition. And there was a paper from 2001 or 2000 at NeuroBOLT from people I know who were solving inverse problem for MEG. And they did the following. They first trained the neural network on, because forward problem is very easy to compute. You can specify, okay, here's my current in the brain. It's right here. You know the answer. Inverse is like multiple answers and blah, blah, blah. So you can train a model, neural network, that was 2000 or 2001. You train a neural network to take the electrodes or squid sensors and predict where the source is. And this is your starting point for classical optimization. And then you tune it so that it matches exactly the measurement. And like they got really good results. Now with diffusion models, you can solve or replace a lot of those inverse problem solvers with diffusion models. That okay, so here can we do something like that? Use both fMRI and EEG to reconstruct it. Don't leave.
No, I was just checking. I was like, I can't find where this meeting is anymore. So I was like, did I?
Oh yeah. Room is there.
Yeah, it's there somewhere. Okay.
Yes, and this little pencil there tells me.
Yeah.
So people, I don't
Oh, there
know
you
you can
go.
hear us online, and Brett didn't.
Yeah, I didn't.
turn it up. Okay, well, anyways, I I think it's like at least it inspires a lot of conversation, right? Maybe it's not.
Yeah. I mean, I think it's an interesting paper. I would have done things differently, but perhaps this. There's something to learn as well about NeurIPS as a conference. The fact that this got accepted, that you don't have to, like, you can kind of just do like a proof of concept, like what this feels to me, and if you just package it the right way.
Yeah.
It can still get published.
That's about any human endeavor.
Maybe
Look at nature papers.
as an opinion piece, maybe. Kind of.
I don't think it's an opinion piece. They've got results.
Well, they got some results, but it would be better if they had an opinion, and then they said, "Oh, here are some results also."
I mean, I don't so much agree with that. I just think that they make a lot of claims that are not substantiated. Like I would have, if I were writing this paper, I would have held back on some of those claims, but it might have also not been as easy to sell the paper, which is
Just ongoing around. Okay,
sorry.
interesting for people who connected remotely. Maybe we have a talk in 8 minutes at DMAP by a person who had schizophrenia or has schizophrenia and still succeeded in life. So that's going to be interesting. Their story of and I think it's over the video, but still. That's why I don't know, TJ, if you want to join there. Thanks, and I'm stopping the recording. Thanks for online people, anyone who bothered to listen.